We're going to talk about even and odd functions. So a function f is even if for every number x in the domain the number negative x is also in the domain, and f of x is equal to f of negative x. So for example, if we have the number 5 in the domain, then we'll also have negative 5 in the domain. And when we evaluate the function at the number 5, it's going to be equal to the function evaluated at the number negative 5. So if f of 5 is 3, then f of negative 5 will also be 3. Turns out that we've actually seen even functions before. The graph of an even function is symmetric about the y-axis. So what that means is, if you see a function and you look at the y-axis, which is right in the middle of the plane, if what you see on the left of the y-axis is a mirror image of what you see on the right, then it's symmetric about the y-axis, which makes it an even function. Let's talk about odd functions. A function f is odd if for every number x in the domain the number negative x is also in the domain, and we have the following property, that f of negative x is equal to negative f of x. So before, with an even function, the negative inside went away. Let me scroll back up. You see how I have a negative x here, but that goes away here. This time, when we have a negative x, the negative goes on the outside of f of just x. So if we have the number 5 in the domain, then the number negative 5 is going to be in the domain. And let's say the function's value at 5 is 3, then the function's value, so let me write this down so we can see this. So let's say 5 is in the domain, that implies negative 5 is in the domain. And just for an example, if f of, let's say, negative 5 is 3, then f of 5 is going to be negative 3. So with an even function, we would get the same number. We would get both a 3 here. But you see, when I plug in the negative here, I get the negative of f of 5. So if f of 5 is negative 3, then the negative of that would be 3. So f of 5, the negative of f of 5, be negative of negative 3, which is just 3, which is exactly what f of negative 5 is. That is this rule here. And we have seen odd functions before. The graph of a function of an odd function is symmetric about the origin. So the graph of an odd function is symmetric with respect to or about the origin. So remember what that looks like. A graph that's symmetric about the origin means that whatever you have, let's say here, it will be rotated and put down here as well. So you'll have exactly the same thing here and here. And anything you have here will be down here, but rotated. So another example. Maybe I can put it here. So like this graph here, what I have right here, if I rotate it, there's going to be a mirror image on this side here. Now this needs to go right through the origin. So let me make it a little bit bigger. Okay, so that's the idea of being symmetric about the origin. So we're going to learn how to test if a graph is symmetric about the origin, which is just by looking at it. And we're going to also test the equation of a graph to see if it's symmetric about the origin or symmetric about the y-axis. In other words, if it's even or odd. And how we're going to do that is we're just going to look at these properties here. This property and this property. So let's look at some examples. Let f of x equal x cubed. Is the function even, odd, or neither? I went ahead and graphed this function, x cubed. Let's look at the graph a little bit bigger so maybe we can understand why we get this picture. F of x equal to x cubed. Let's plot some points. If x is 0, then 0 cubed is 0. So we have a point through the origin, which you can see that I have that. If x is 1, then 1 cubed is 1. So I have the point 1, 1. And here at 1, 1, I have a point. If x is equal to -1, -1 cubed is -1. So I have the point -1, -1. So here I have a point. We can do some other points as well, just to make sure that the graph is correct. If x is equal to 2, then 2 cubed is 8. So I should have a point at 2, 8. Here's 2. And look, this is going up. We don't see past 6, but it looks like it's going to go through 8. And of course you can pick stuff between 1 and 2 and cube it, and you'll see that you're going to land on this line. And if you choose -2, well, if you cube -2, you're going to get -8. And you can see that this picture kind of depicts that. Now, we want to show that this graph and this function, so the function being f of x is x cubed, we're going to show that it's odd. And this is how we're going to do that. What we're going to show, or what we're going to try to do, is plug in -x into our function. So what happens if I plug in -x? Well, I'll get -x cubed. Wherever I see an x, I'm plugging in -x, and I have to put these parentheses here because I'm plugging it into right here. If I don't put the parentheses, especially if you put it in a calculator, the calculator will understand just the x being cubed, but here we want the -x to be cubed. So if I take -x and cube it, it's the same thing as multiplying it 3 times, which is going to be negative, because a negative times a negative is a positive, and then another negative, so it's -x cubed. Now what we're going to do is we're going to look at this and compare it to our original function. What's the difference between x cubed and negative x cubed? Well, this is the negative of this function. So what we've seen is that f of negative x, which is negative x cubed, is negative f of x, because f of x is just x cubed. So if I multiply it by a negative, then I have this negative f of x, which tells me that we satisfy this property here. F of negative x is equal to negative f of x, and that shows that the function is odd. This implies the function f of x equal to x cubed is odd. And like I said before, we could also just graph it, and we would see that the graph is odd because it's symmetric about the origin. So whatever is here, rotate it and put it down here, you can see that I would get the same thing. Let's try another problem. Let f of x be the absolute value of x. Is this function even, odd, or neither? So here I've graphed the absolute value function. Let's plot some points just to show that they coincide with this graph. If I let x be 0, well, the absolute value of 0 is 0, so I have a point at the origin. If you plug in 1, the absolute value of 1 is 1, so you have a point at 1, 1. And then also at 2, 2, if you plug in 2, and 3, 3, 4, 4, and so on. And if you plug in negative 1, you're going to get the absolute value of negative 1, which is 1. So that's why you have a point at negative 1, 1, negative 2, 2, and so on, because you're just taking the absolute value of it. So this graph makes sense. It's a V-shaped graph. Now, notice that this V-shaped graph is symmetric about the y-axis. Here's the y-axis. So that tells us, just by looking at the graph, that the function f of x equal to the absolute value of x is even. Okay, so just looking at the graph, I can say the function is even. Now, if I didn't give you the graph and you didn't know what it looked like, you can just use this test where we plug into the function negative x and see what we get out. So if I plug in negative x, wherever I see an x, I'm going to put negative x. So I'm taking the absolute value of negative x, and the absolute value always gets rid of the negative. So we're going to get just x. The absolute value of x, because this negative goes away. So you can see when I take the absolute value of a negative number, it would be the same thing as taking the absolute value of a positive number. For example, if I put negative 1 in here, well, that would just be the same thing as the absolute value of positive 1. Or if I took the absolute value of negative 2, that would be 2, which is the absolute value of 2. So anytime you have a negative inside an absolute value like this, you can just get rid of it. And now this is the original function, right? So this tells me that f of negative x is equal to my original function. And this was the property of even functions. So this implies that f is an even function. Okay, the next function I'm going to give you is x squared plus 5x plus 3, and I want to determine if the function's even, odd, or neither. I have the graph below, but I want to do the test algebraically first, and then look at the graph and make sure that my answer of it being even, odd, or neither corresponds to the graph. So what do? I just plug in negative x into my function. So wherever I see an x, plug in negative x. So negative x squared. if I take negative x and multiply it by negative x, negative and negative make a positive, and I get x squared. Anytime you have an even power like this, you can just get rid of the negative inside. So this is x squared, and then 5 and negative x make a negative 5x plus 3. So this is what f of negative x is equal to. Now compare it with the original function. Are these the same? Well, no, they're not the same, because here I have a positive 5x and here I have a negative 5x. So that tells me f of negative x is not equal to f of x. So this is not an even function. Is it possible for this function to be odd? Well, if it's odd, then we need to show that f of negative x is that equal to negative f of x. So in other words, if I take this function and multiply it by a negative, do I get this function here? And the answer is no. And that's because negative f of x is equal to the negative of x squared plus 5x plus 3, as you can see. All I'm doing here is f of x, putting a negative on the outside, so I put a negative on the outside of this piece. And what I get is negative x squared minus 5x minus 3. So that's the negative of the function. And you can see these aren't equal. I do have the negative here, but now this is negative and this is negative. So it's not even and it's not odd. So this piece that we were looking for, this is not true. So it's neither. Now let's look at the graph. So here's the graph of the function, and we're going to learn how to graph such a function. But you can tell, if I draw a line along the y-axis, you can see that whatever's here is not the mirror image of this. So it is not symmetric about the y-axis. Also, whatever is here, which is just this piece of a line, if I rotate it and put it down here, we don't have it. In fact, I have this valley here, and so I should have a valley here. And this piece here is not rotated here, so it's not symmetric about the origin either. So it is indeed neither. It's neither even nor odd.